Hey, welcome back. Today, we are going to get our hands dirty with a real classic electronics problem, one that's right at the heart of pretty much all our devices. We're going to break down a transistor amplifier circuit piece by piece. So have you ever really thought about it? How does a tiny, tiny electrical signal, say from a microphone, get turned into something powerful enough to drive a huge speaker? I mean, how does that happen? Well, the answer is amplification, and we're about to see exactly how it works. All right, let's get into it. Here's our mission for today. We're going to find the input voltage and the base current for this common emitter amplifier. We're kind of working backwards, actually. We know the output, and our job is to figure out what tiny little signal kicked the whole thing off. Okay, so any good investigation starts with the facts, right? The givens. Here's what we know. We've got a collector resistance, RC, of 2 kilo ohms. The base resistance, RB, is 1 kilo ohm. We're seeing a solid 2 volts at the output, and, super important, our transistor has a current gain, or beta, of 100. This is our starting point. Now, before we jump right into the calculations, let's talk about our toolkit. There are really just two key concepts, two formulas that we're going to need to crack this thing. And once you get these, the how of it all becomes so much clearer. First up, you guessed it, the absolute bedrock of all electronics, Ohm's law. You know this one. Voltage equals current times resistance. It's a simple relationship, but it is so powerful. We're definitely going to be using it a couple times today. And here's the magic ingredient, the whole reason a transistor works as an amplifier. Beta. That's the current gain. All this number tells you is how many times the transistor multiplies that little input current at the base to create the big current at the collector. It is literally the heart of amplification. All right, toolkit is ready to go. Let's start our investigation. We're going to begin on the output side of the circuit and find our first unknown, the collector current, which we call IC. So how do we find that current? We go right back to Ohm's law. If V equals I times R, then it just makes sense that I, the current, must be V divided by R. For our circuit, that means the collector current, IC, is just the output voltage divided by the collector resistance. Okay, now for the easy part. We just plug in the numbers we already know. So that's 2 volts for our output voltage, and we're dividing that by 2 kilo ohms, that's just 2,000 ohms, right, for our collector resistance. And the math gives us 1 milliamp. There it is. That's our collector current. So the first big piece of our puzzle is now in place. We know the amplified current that's flowing through the output of this thing. Excellent. So now that we have the collector current, we can use that magic number, the transistor's beta, to figure out the tiny little input current that started this whole chain reaction. We're talking about the base current, IB. And this comes straight from the definition of beta we just talked about. If beta is the big collector current divided by the small base current, you just flip it around a little bit, and you get that the base current has to be the collector current divided by beta. Simple as that. Okay, so we just figured out the collector current is 1 milliamp, and we know from the givens that our beta is 100. So we're just going to divide 1 milliamp by 100. And we get 10 microamps. Now just think about that for a second. A microamp is 1 millionth of an amp. This is the incredibly small little trickle of current that's controlling that much larger 1 milliamp current at the output. That's the amplification we're talking about. Okay, we are on the home stretch now. We've got the input current, IB. All that's left is to use Ohm's law just one more time, this time on the input side, to find our final unknown, the input voltage, VI. Yep, back to our good old friend Ohm's law. The input voltage is just going to be the base current, which we just found, multiplied by the base resistance that we were given right at the very beginning. So let's plug in the numbers. That's our 10 microamps for the base current, and we're multiplying that by the 1 kilo ohm base resistor. And that gives us our final answer, 0.01 volts. Wow, that's it. That is the tiny input signal voltage that's driving this whole amplifier. Okay, so we've crunched all the numbers. We've got our answers. But what does it all really mean? Let's step back for a second and look at the big picture, because these numbers tell a really cool story. So here's a quick summary of our whole investigation. It's pretty neat, right? We started with just a few pieces of information, the output voltage and our component values, and from that, we were able to systematically figure out everything else that's going on in the circuit. And this, right here, this is the aha moment. Just look at this comparison. We put in a teeny tiny signal of just 0.01 volts, and what came out? A powerful 2 volts. That is amplification, right there in black and white. And if you want to put a single number on that, just divide the output voltage by the input voltage. You get a voltage gain of 200 humvits. Our little input signal was magnified 200 times. That is incredible. So at the end of the day, what we've really shown here is the core principle of how a transistor amplifier works. A very small signal at the input controls a much, much larger signal at the output. That is the absolute essence of amplification.
And that leaves me with one final thought for you, a little challenge. Based on the formulas we just walked through, what do you think would happen if we doubled that base resistor? Would we need a bigger or a smaller input voltage to get that same 2-volt output? Think about it, and if you can answer that, you've really got this down. Thanks so much for joining me.